Thanks, Ryan. Shall I go ahead and share my screen? My introduction is actually my second slide.
Perfect.
Are you seeing my title slide, hopefully?
Yep, I am.
Yep. Okay, great. So everything that we're going to do today, hopefully, is going to be within this browser. So that should keep it pretty smooth. Thanks for coming to my show and tell. This is quantum computing for the qubit curious, and what we're going to do is just take a really gentle excursion through quantum computing, and actually play around with some notebooks and run some real jobs on a quantum computer in real time. So hopefully this works out well. So, quick intro. My name is Glen McLaughlin. I work in research technology services. Our coordinates are HPC at gw.edu. That's our website. And you can get in touch with my team, Research Technology Services, RTS Help at gw.edu. And if you really want to spam my inbox, that's my email address right there. Um, I've been uh, I've been working with research technology services or adjacent to research technology services for almost 20 years now at GW, and played a pretty big role in the HPC effort. And yeah, so if you've seen me around campus or been in one of my talks before, it's probably in that context. But this is going to be a little bit different. So what should you expect from this talk? Hopefully, we're going to have some fun. Maybe learn some things, a little bit of physics. There'll be no pseudoscience, no string theory, no many worlds. Although I repeat myself, we're going to, like I said, learn about quantum computing in the cloud. See some of the toolkits, or at least one of the toolkits that's available for developing quantum circuits. And like I said, see these results in real time. I am not researching quantum computing. I'm not going to present any results. I have not solved any problems. I'm merely a hobbyist. This is, some folks like to 3D print. Some folks like fly fishing. This is just, it's sort of a weekend thing. And actually, it's funny, the way I even started looking into this is a couple of people, a friend of mine at work, Rabiel Iqbal, had some really interesting conversations. Uh, um, and also my son. At any rate, this is sort of, in some sense, this is dedicated to them. What are the use cases for quantum computing? We hear a lot about it. There's a lot of uh, a lot of hype about quantum computing and what exactly it's going to do. And I realize that this is a university audience, and probably some of you have a fairly good understanding already. But for the rest of us, some of the use cases for quantum computing realistically are, well, factoring very large numbers. Okay, great. Well, why is that useful? Well, that's particularly useful in terms of encryption. Um, there are quantum algorithms for searching unsorted lists of data and getting results that are by far an advantage over classical computing, but probably not as good as you would expect. I sort of alluded to already, but one of the more practical uses of quantum computing is breaking encryption. And so maybe you have heard a discussion of the store now, decrypt later posture, where you may have, for example, large corporations, state actors, interested parties who are harvesting encrypted data now that's protected by RSA. It's protected by prime number factorization or elliptic curve encryption. But they know that at some point in the future, quantum computing is going to become a viable alternative to, a viable option. And at that point, all of these data that have been harvested and encrypted, well, people will be able to rifle through those. So that's a good reason to start looking at TLS version 3 now and using quantum secure algorithms. One of the other use cases, in the one that I'm going to focus on here, is that developing your physics intuition, your quantum mechanics intuition, is now free. Well, free with an asterisk. It's free up to your monthly limit until the billing cycle renews. But so here's some other things. This is AI generated. I asked AI, what is quantum computing? Who's interested in quantum computing besides physicists and chemists? I think the interest there should be obvious, but for those outside of quantum computing, um, I have not verified the authenticity of this, but who knows if one of your fields of research falls in these areas, maybe this might be even more relevant. Okay, so what's actually stopping us from embracing quantum computing? Like I said, we've heard about this quantum advantage, how it's supposed to speed up calculations and take calculations which ostensibly would take 300 trillion years and do them in a few hours. Well, why don't we have these in our MacBooks yet, or why aren't these in our iPhones? So, well, that's never going to happen. At least not in the foreseeable future, not with the sort of physics and understanding of engineering that we currently have. But so with that context, what are the practical barriers for quantum computing for a researcher? Well, number one, quantum states are very fragile. Um, Entangling two qubits, which I'll explain what those are shortly, but entangling two qubits is not easy. Try it at home, right? It requires an environment that is essentially near absolute zero and effectively vibration free. We don't want any thermal or we want to minimize as much as possible thermal vibrations, obviously acoustical, and keep the system as still as possible for as long as possible. To try to get in an entangled state, to remain in an entangled state for hundreds of milliseconds is right now quite an engineering feat. So they're very fragile, susceptible to environmental noise, very expensive to operate, as you would imagine. And I'm going to harp on that a lot later as I go through this. I'm astounded by the price of these things. And at this point, the qubit count is still effectively very small, at least in the free tier that we're going to be looking at. We're going to be talking about quantum computers that have 130, 150 or so physical qubits. Let's see, how are we doing on something here? Actually, pretty good. So you're all familiar with Schrodinger's cat. I think a quantum computer presentation has a requirement to discuss this, but the idea of Schrodinger's cat. What was Schrodinger's cat? Schrodinger hated cats, hated them more than he hated the way his equation was being interpreted. And to illustrate what he thought was, and I think you'll agree, is an absurd conclusion. He imagined this thought experiment, this thought experiment where you place a cat in a box, and in this box there is a vial of some radioactive or of some poisonous gas, and there's also an atom that's set up so that when it decays, it triggers a hammer that will then break the glass, release the poison gas, and then kill the cat. In a quantum world, right, with our quantum intuition, we understand that this atom is in a state of both being decayed and not decayed at the same time. And so therefore, there's this sort of contradiction where you try to connect that to a macroscopic physical system, right? We know that it's absurd that the cat both be alive and dead at the same time. Although in the quantum world, this is actually what we see. So I want to challenge you here for a moment and sort of develop your intuition about what this looks like. So let me take a sip of coffee here. So I have a similar sort of thought experiment, which I think should also sort of challenge your intuition and startle you a bit. But I want you to imagine that you have 1,000 people And so hopefully you can see my pointer here. Um, I know that there used to be a little trail I could turn on, but at any rate, so imagine these are sort of tables or filters that 1,000 people are going to walk past. And out of this 1,000 people, we have equal mixtures of left-handed and right-handed people, and people who happen to be whose blood type happens to be O positive or O negative. So we're just going to assume a homogeneous mixture of these traits within this population, right? So now we're going to have 1,000 of these people who pass by. On average, if we repeat this experiment multiple times, right? Um, well, I'm getting ahead of myself. So let me explain what the filters are here. So I have a left-handed, right-handed filter. What this is it's basically a table or a turnstile that they pass through. This passes left-handed people, and it tells right-handed people, go sit down, go wait. So only left-handed people get to pass. This filter is flipped around. This filter only passes right-handed people. So, of course, as the population passes this filter, here we only have left-handed people. We keep going through the filter. Now, this is a right-handed pass filter, and so therefore nobody makes it through, right? It's it's pretty straightforward. Basically, we have these two filters that are acting like a gate that are just stopping the stream of people. However, what happens? Actually, I should pause here and ask if there are any questions. Okay, good. So what then happens? So here's where we're going to challenge your intuition. What then happens if we do two things? We insert a blood type measurement in between our handedness measurement, and I tell you that these are quantum people. And don't worry, I'll define that later. So how many people do we expect to pass through? Classically, all right, according to our classical intuitions, according to classical physics, we would expect zero people to pass through. It doesn't matter that we inserted a blood type measurement in between, that's irrelevant. However, that's not what happens in a quantum world. In a quantum world, it turns out that actually 125 left-handed people suddenly make it through. Um, oh no, I actually, sorry about that. I should have fixed this. Here, this is editing in real time. So it's actually here, the intuition here is 125 right-handed people now pass through the this filter. And so what's happening here? What's happening is that it's true, only left-handed quantum people are allowed to pass through. However, when I put these people into when I make a measurement of their blood type, that puts them into a superposition of both being left-handed and right-handed again. Because, well, what I didn't tell you previously is that these are conjugate quantum variables. So they cannot both be well defined at the same time. So when I force them into a state of having either O positive or O negative blood type, that puts them into a superposition of being both left-handed and right-handed. It's not just math. It's well, I mean, the math is actually fairly simple, but that's because this is what physically happens. And so although we expect there to be zero right-handed people passing through this filter classically, because we reintroduce both left-handed and right-handed states, those right-handed states are there to be passed through the filter. Anyway, so the act of, like, just to summarize, the act of measuring, observing a quantum object fundamentally changes it. When we measure handedness, we force the quantum people to be in a superposition of being O plus and O minus at the same time. They can't be both left and right, left, right, or right and have a well-defined blood type. Actually, let me take another start at that. They can't be both have a both handedness and have a well-defined blood type. They can either have a well-defined handedness or they can have a well-defined blood type, but not one or the other. So it turns out that the fact that we can put states in superpositions gives a solution space for quantum computers that's much, much larger than for classical computers. Not only that, we can search that space. Oftentimes, it depends on the problem. There's not a general rule of thumb, but we can often search that space faster than we could search it classically as well. So, okay, I'm going to shift gears a little bit, and you're going to see this notation over the next few slides. So I want to explain what it is. Traditional computers use bits that are either in a state of 0 or 1. We know that.
Slides are not, by the way, Glenn.
What's
We're
that?
not seeing your slides. We're seeing you now. You took your slides off
Oh no, how long ago was that?
just a minute or two ago when James
I
walked
think we're
into
up
the
to date.
room. So I thought it was something to do with that. Oh, there we go.
Okay.
Yeah, we saw that slide.
All right. And you saw this?
No.
We did not see the slide, but that's what you described.
It's fine. Yeah, that's right. So anyway, yeah, so this is where we were. So like I said, we understand what traditional computers, or we have some understanding at least that information is encoded in traditional computers as ones or zeros. Quantum computers, like I was just saying, use qubits. The quantum bit is the analog for quantum computers, and that can be in either a spin 0 state, which is a spin down. So you can think of it like this picture here, where if we have a magnetic field pointing up, which is not here, but just imagine there's a magnetic field pointing up, the spin 0 state is anti-aligned with the magnetic field. And if we give it just a little bit of energy, we can nudge that, whatever it may be. It's just an abstract qubit. Let's call it an electron. It could be a neutral silver atom. It could be a variety of things. That's one of the beauties about qubits. It doesn't really matter for our purposes what the physical realization is. But if we give it just a little bit of energy, we can nudge this dipole in the direction of the magnetic field. It's not a very stable state, but we can get it there. We can also get a superposition of both up and down spin states at the same time. And so what you see here, let me define what this strange notation is. This is essentially how physicists represent vector spaces. It could be a finite vector space. It could be a continuous vector space, like a function field. But essentially, this is we call it a ket. It was named by Paul Dirac. He came up with a notation to explain to basically simplify working with inner and outer products and Kronecker products. So this is called a ket. It just simply represents a vector. This is the 0 state, or the 0 ket. This is the 1 ket. We call this the phi plus ket, and the phi plus ket is just simply a superposition of both the 0 and the 1 ket. But anyway, I'll explain more later. But if you need to go back and make contact with a picture in your mind of what these kets are representing, just think, okay, the 0 ket is a sort of a particle anti-aligned with a magnetic field, and the 1 ket is a particle aligned with a magnetic field. Simply like you might imagine, okay, a 0 state in a classical computer is a discharge capacitor, and a 1 state is a charge capacitor. It's the same sort of thing. So when you put two or more qubits together, you get these. You can use these special quantum operations, and you can get these really interesting entangled states. The operations look like, well, H or X here, and I painted them those colors because in the framework that we're going to use to actually develop these circuits, this is what they look like. So at any rate, I'll explain what the X and X in the H gates are in a few slides, but suffice to say, they are like the sort of classical gates that you might see in a classical computer, like an OR gate or an exclusive OR gate or an AND gate, a not AND gate, that sort of thing. Now, the interesting thing about entangled states is if you measure one particle in an entangled state, you immediately get information about all of the other states of the other particles that happen to be in that entangled state. So in these demos that we're going to look at, we're only going to look at 2 qubits, so it's going to be the smallest entangled state that you could get. But in principle, you could, well, in principle, if everything's working well, you could get an entangled state with over 100 qubits in the quantum processing units that we're going to be looking at. From a physics perspective, one of the sort of problems or paradoxes that entangled states seem to present, and you may have even heard of this as the Einstein Rosen-Podolsky paradox. Um, it was it was realized somewhere, I guess, what was in the 40s or 50s, that there are some disagreements with quantum mechanics in the theory of relativity, and Einstein wanted to bring some of these disagreements into focus and came up with this argument, the EPR paradox. So, in very hand wavy terms, where the paradox comes from is it looks like when one makes a measurement of an entangled state, suppose I have two particles that are entangled. I could then carefully separate them. I could put one of the particles on the moon, let's say, and keep one here in a lab on Earth. According to quantum mechanics, if I make a measurement of one particle, then the other particle instantly assumes whatever state the other particle has decided. It's it appears as though that violates the speed of light. So we have information. It would appear as though information were being transmitted faster than the speed of light. Even if that were the case, nothing useful could be done with that information. I think that's how the philosophers sort of hand wave that around. But it is sort of an interesting domain in physics right now, exactly how quantum entanglement and the theory of relativity comport with one another. But anyway, we'll keep going. So here's some things to know. We're going to be looking at quantum circuits. I think I mentioned this on another slide, but quantum circuits are the foundation of quantum computing. When we start with a quantum circuit, if we have, let's say we have 2 qubits or 3 qubits or 100 qubits, by convention, we always start our circuits, which is a bit of a misnomer too. They're not actually circuits. They're laid out linearly as opposed to an electrical circuit. But we always start with all of our qubits in the 0 state. So just think of, we have some number of qubits, n qubits, that are all pointing anti-parallel to a magnetic field, if you will. And actually, I'm going to skip ahead here. So some of the gates that we're going to look at, I'm going to focus on the Hadamard gate at first. That's one of that's a really interesting gate. It's also going to be the subject of the first demonstration that we look at. So what a Hadamard gate does is it will take a qubit in the 0 state. So again, thinking of some particle pointing anti-aligned to a magnetic field. It's going to take that state and it's going to project it into a superposition of both a down state and the up state. It's actually equal mixtures. So that's why we have a normalization of 1/2, by the way. When we square this, the normalization has to add up to 1. But you can ignore this, the normalization factor. What's really important is that once we apply a Hadamard to a 0 ket, we're going to end up with a superposition of kets. How do we construct multiple kets? It's actually pretty straightforward. So let me just walk through this sort of quickly. Suppose, take a look at the diagram that we have here on the right. This is a very simple circuit. We read it from left to right. We have 2 qubits, Q0, it's our 0 qubit, and Q1 is our first qubit, which is actually our second qubit. We're starting from 0. The way we would read this diagram, going from left to right, is that first, qubit 0 sees a Hadamard gate. So what actually happens to this qubit? Well, the way we would write it is this. We're choosing little endian because the API that we're going to be working with uses little endian, but this doesn't really matter either. If you want, you could lay these out Q0, Q1. We just happen to be going in reverse order. I wanted to keep it consistent with the API we'll be looking at, but we'll have 2 kets, 2 qubits that are both in some state. We don't know what it is yet, but For a shorthand, we can write them like this, just using sandwiching them inside one single ket. So that's what this notation looks like. So when we start out all of our qubits, both in zero kets, we have the 0, 0 state. Now recall Q1 only applies, or the Hadamard only applies to Q0. So our Hadamard applies to our Q0 qubit, turning it into a superposition of the 0 state and the 1 state. And then when I distribute my Q1 back into my expression, I end up with two terms that look like this. A state where both particles are both pointing down, or a state where one of the particles, the Q0 is pointing up, but Q1 is pointing down. That's a little confusing. But anyway, that's essentially how that works. Now, uh, I if I were a gentle presenter, I would pause here and ask if there are any questions. But what I want to do is just dispense with all of the math and skip right ahead and show you a very simple diagram that will allow you to skip at least one semester of linear algebra. So,
Your definition of simple cracks me up, Glenn.
well, actually, it looks busy, but once I explain how it works, you'll say, "Oh, I get it. This is just a map." This just shows you how to start from the North Pole here, where our zero state is. Remember, we always start at the in the zero state. So we're gonna look at what these three different operators our exchange operator, our phase flip operator, and what the Hadamard operator that we just looked at in a little bit more detail. We'll see what effect these have on a qubit. So what we're going to do is we'll start with a qubit in the zero state. It's pointing due north. And if I were to apply a Hadamard to that qubit, what that's telling me is I simply follow the green line to wherever it goes. I reflect about the dotted line. So, okay, if I'm going to apply a Hadamard to the a zero state, I end up in the phi plus state. If I were then to apply a phase flip operator, what does that do? That actually just brings me from a phi plus to, well, you can't really see it, but it's a phi minus state. If I were then to apply another Hadamard operator, that would take me from the phi minus state to my one state. Of course, I could simply replace all of those transformations, the H, the Z, and the H, which are just matrices, by the way. I could replace the product of those three matrices with one direct operation where I go from the zero state to the one state just by applying my exchange operator. And you can see how you can hit every other points. All of these points, by the way, I should have mentioned this at the outset. Sorry, this is my first time through this talk. All of the points on this block circle represent available states that a single qubit could occupy. And these are the different ways that we could get the qubits into those states. Why is that important? Because when we're doing quantum computations, we need to be able to hit all of these states. And it's through these operators that we can get there. Right. So anyway, this is what replaces all of the math here. I didn't define what the Hadamard is, but it's okay. You can reach out to me or you can Google it just as easily. But yeah, so effectively, that's how that might work. And again, just to start again, if I were to apply, let's say, the exchange operator on the zero state, I end up with the one state. I apply the phase flip, I end up with the negative one state. If I apply the exchange operator again, I get to the negative zero state. So, all right. So anyway, any questions about that? Because I think I need to speed up a little bit. Good news, you don't really need to you're not going to be doing a lot of these calculations in your head. So I think we can move ahead without any danger. So there are two special cases. We're going to look at three demos online. There are two special cases. One of them is a coin toss, a quantum coin toss, which I'm sure is pretty intuitive. The other special cases that we're going to look at are creating Bell states. I've already shown you one of the Bell states, and then we're going to be looking at Brover's diffusion. And Brover's diffusion, well, let's just go through these. So I've shown you one of the Bell states that we're going to set up. We're going to set up a circuit that looks like this. and we'll get the phi plus state. And then we're going to get three similar circuits that will give us the phi minus and then the C plus and C minus. Um, I've already mentioned what it means to be an entangled state, so I'm going to skip through this one. And by the way, these are what the Bell states that we're going to produce, what they're going to look like. And what we're going to find is, what we're going to ask is, well, we tell the quantum computer to create a Bell state, and then we measure that state. If it gives us what we expect, we say that there was a success there. If we do not measure the Bell state that we prescribed, then we would say that's an error, and that's how we're going to measure. That's one of the ways that we'll measure the error rates that we see. Let's spend a couple more minutes on Grover's algorithm because I think this is might be unfamiliar to some of you. By the way, Grant Anderson on 3 Brown 1 Blue does a couple of great videos on Grover's search algorithm. So much better than I could do, in a brief talk here, or even a much longer talk. But Grover's algorithm is it's a search algorithm for searching unsorted lists of data. It's sort of the quantum analog of finding a needle in a haystack. So imagine, for example, that you're trying to find an entry in a very long list of data. Let's suppose it's a set of data that's non-indexed, a million entries long. You're trying to find a particular entry. On average, you could get really lucky and find it the first time on your first guess. You could be really unlucky and you wouldn't find it until your 1 millionth minus one guess. At that point, you don't really need to guess anymore. But on average, it's going to take you 500,000 guesses to find this entry in this unsorted list of a million elements. By Grover's algorithm, a quantum computer would only take about 1,000 guesses on average, or about 2% the number of guesses that a normal computer would take to find the correct entry in this unsorted list of data. And to scare you, this is what Grover's full circuit looks like. It's a series of Hadamard gates. I should say this is a 2-qubit Grover circuit, so this is actually a very simple circuit. 2 Hadamard gates, an exchange operator. There's some more exotic gates here, which I'd be happy to explain. If there's time, I can come back and explain what these mean. What you haven't seen before are these gates at the very end. This simply means stop and take a measurement. And the third rail here that you didn't see before either, this would be what a classical computer would read out as the state of all of the state of these qubits if a measurement were made at that particular time. So it doesn't affect the calculation. It's not really important. It's just it's there to let you know that when read out, this is what the classical result would be. I guess I should mention also that we never actually make a measurement of a quantum state. Well, let me make sure that's not what we measure. What we measure is we measure a voltage. We measure a classical result that is that represents the quantum state that that was selected for, at least in the case of the Bell states or for whatever the correct entry may be for Grover's algorithm. Okay, so let's get to the fun stuff. Last 20 minutes or so. So for this demonstration, I used a few free resources. I made ample use of IBM's Quantum Cloud, which I'm going to focus on here. Everything I did and what we're going to look at here was also done using the free tier of Google Colab, which I also connected to my Google Drive. And I also made ample use of the AI agent that's embedded in Gemini that's embedded in Google Colab. It's wonderful. So this is where you can find IBM's Quantum Cloud. You can go ahead and go there if you want. You can just take a look at it now with me while as we discuss it. But IBM's Quantum Cloud offers you access to actual quantum processing units. It will offer a free tier, and I'll talk about the different tiers in an upcoming slide. But what it does is offers 600 seconds of free QPU time every 28 days, which is actually pretty good because it turns out that the QPUs that I was using, should I had gone over my 10-minute limit, it's $1.60 a second. So you can imagine that is you're playing a dangerous game when you give IBM your credit card. Um, so you also get access to Qiskit, which is what we're going to take a real deep dive into. Qiskit is the API that allows you to create quantum circuits and both run them on simulated form, which we're going to run the simulations in Google Colab. And then once your simulations are working properly and they're working to the way that you expect them, then if you're feeling really brave, you can go ahead and run those on a real quantum computer, which will do that too. So okay. Um, so the IBM pricing tiers, I'm going to skip this actually. We can come back and talk about this. Suffice to say, though, there are tools that can help you from going into serious debt, but at any rate, so this is well, this is not any of the three computers that we're using here, but I thought this is a real beautiful image that I stole out of an archive article. Um, uh, so the IBM's free tier gives you access, and we'll see this when we log into our account. IBM gives you access to three free computers. There's Marrakesh, there's Fez, and there's Torino. They're all slightly different. Torino has fewer qubits, and so you expect it to be less accurate. And I will be able to show that in the results that we see too as well. Um, okay, maybe I want to mention a few things about Qiskit. Qiskit is an end-to-end software stack for quantum computing. It is hardware aware, so meaning the compiler, or at least in the case of quantum computing, we talk about the transpiler. Qiskit, or the I think I think I'm not being overly broad when I say that, but Qiskit is aware of what particular hardware you're going to be running on and is able to compile your quantum bit code or byte code into code for that particular application. Um, Integrated into IBM Quantum Systems. Although I'm running Qiskit externally in Google Colab, it is possible to run it in IBM's on my IBM account, but I felt that there was a safer firewall if I just did it completely separately. And you can also do such things as, because it's hardware aware, you can do such things as select runtime tunables and optimizations. And we'll play a little bit with that. Although in our case, optimization basically says, well, the transpiler is aware that these qubits aren't working very well, so we're just going to not use them. It's sort of like when bad memory is found in the kernel, we'll isolate that memory and not use it. Um, so yeah, I mentioned before, quantum circuits are the foundation of quantum computing. Essentially, they're the staff rather for music, right? So everything that we're going to be doing is going to be involving quantum circuits. And with that, I want to see if I can't. Oh, that's a little too far. Oh, I think I have to exit full screen. All right, can you guys still see my browser?
Nope, we see you.
Okay.
Still see you.
Okay. There we. Yep. How about now?
Yep. And just to let you know, you have 15 minutes.
Okay, I'm going to let me speed this up a little bit. So let me go ahead and get signed in. So here's IBM Quantum Platform. Let me get signed in, and so this is what the interface looks like for IBM uh, Quantum Cloud Platform. So here I can take a look at the instance types that are available, or rather the instance types that I've created. I've only got one here so far. I can take a look at the resources. These are all of the jobs that I've been running. You can see that I ran a few this morning to make sure things are working correctly. Um, let's see. Did I show you compute resources yet? I think so. Oh yeah, actually, I'm sorry, I misspoke. So here we can see the different quantum or different QPUs that are available by IBM, and of course these are the free ones. So anyway, what I'd like to do is I'm going to go to the docs here, and there's an interesting hello world here, and we're just going to start off with this one. So if you once you get your account set up, um, and you have an instance created, or even before, you don't even have an instance created, you can go here and start looking through the Qiskit documentation. What we're going to do is we're going to take a look at the hello world. Um, I've actually done this ahead of time, but so we're going to start by looking at this hello world experiment, which is very simple. In fact, most of it is just comments and importing packages from Qiskit and Matplotlib. We're going to create a quantum circuit, add a Hadamard gate to it, and then draw it. So I thought we were going to do that. That's interesting.
So collab isn't showing up at all. Oh, there it goes.
Well, yes, but that's not the right.
Ah, huh.
Oh no, this is the worst possible time this could happen.
Did you do a hard refresh on it?
Oh, all right, great. So anyway, so this is Jupyter what should we call it, Colab or Google Colab. You've probably seen this before. In order to run on Google Colab, there are a few things that I need to install, and that's mentioned in the documentation, although it wasn't tuned specifically for Google Colab. So I'll just go ahead and run this. And actually, while I'm doing that, I'm going to get this started as well. So now recall, let's see. This was just taken from the Qiskit documentation. I claim no authorship whatsoever, but we're going to go ahead and run this, and we'll see. Here's the Hadamard gate. Here's the gate that I told you I would tell you about if we had time, although I don't think we will. So what I've simply done is taken their code for these two, and I'm wrapping it up into a noise model, which is going to simulate noise that a quantum computer would normally see. And I'm going to run this experiment over and over again, 8,192 times. And of course, this is just going to be what my simulation might look like. So I've got 10 minutes here. And so essentially what this is a quantum coin toss. So when we're putting let me change this. So now this is effectively a quantum coin toss. In fact, I'm going to erase this gate that I didn't get to talk about. So now it's simply a Hadamard gate on Q0. And so what we would expect is when we measure this state, we're going to get 50% up, 50% down. And as we look at the results, that's basically what we're getting here. So anyway, let me go to the more interesting, I think, notebook. So this is a notebook where we're going to run a few experiments, both simulated and then also run on the real QPU. So this is just sort of perfunctory setup. I like to run this against my Google Drive so that I can save my results there. Actually, I'm surprised it didn't ask me to confirm that again. Here I'm setting up my IBM runtime instance, and this is all boilerplate. When you set up your instance on IBM, it tells you, okay, so this is what the header information needs to look like for your instance. You can see my instance is here. That's not really a security issue, although my IBM token is. This is the token that would connect your account to obviously your instance. Um, uh, let's see, have I run that? Yeah, good. Okay, so now that I've run that, what I'm going to do is I'm going to query my service for all of the available backends. So let's go ahead and do that. And this is going to tell me what backends are currently available. And I see that all three are up and available right now. And this also tells me how many qubits. If I query the number of qubits, I can figure that out as well. Okay, so this is where it gets interesting. I'm going to set this to true. Because if I don't do this, as you can see, I am going to be, I could inadvertently spend money. So let's go through really quickly what our quantum coin toss would look like. It's basically what we just showed you before, although this is just a single qubit. The other qubit became an observer when I got rid of the that other gate, or became passive. So what I'm doing essentially is I'm taking a qubit that starts in the zero state and I'm applying a Hadamard to it, and we should get something that looks like 50-50. See, I've run this already. Let's run my Bell state here. So here I'm creating a Bell state. I've got uh, I'm creating a the phi plus state that I showed you earlier in the presentation. And what I'm simply doing here is measuring against this, I create a phi plus state and then sample a measurement. When I measure both of those qubits, if I find that they weren't in a phi plus state, then I know that the computer didn't do a very good job of creating that state, and I can estimate an error based from that. And then lastly, I'm going to define a sort of version of the three filter, or I guess would be two filter in our case, experiment that we talked about before. It's a version of the three polarizer experiment, which is it's sort of the analog of the left-handed, right-handed O plus O minus experiment that we saw before. So what you're looking at here is, oh no, my labels didn't come out. What you're looking at here is, actually, what are we looking at here? This is the results of the polarizer experiments. The results of this is the polarizer without the third polarizer. This is the result of the polarizing experiment with the third polarizer that puts both states into or puts our quantum person into a mixture of both being left-handed and right-handed. This is our coin toss. Obviously, this is going to be 50-50. And this is uh, the Bell states, that the measurement of the Bell states. Either we should be getting a 0-0 or 1-1. This is our simulated experiment. Let's go back here, and I want to set this to false, and I want to actually run this on a QPU, and we can go here and watch it as it runs. Oh, that's not it. Okay, so when I hit enter, I will be spending money. And in a moment, we should see, I don't think I have to refresh this. Oh yeah, so here we see the jobs are starting. And this is going to tell me roughly how long each job is taking. Um, I say roughly because it's telling me the time in integers. I think when you're spending $1.60 a second, you want to know if it's a half a second or not. Let's see. So looks like we're actually getting results. I realize that I'm really bringing up the cutting it close to time here, but let's take a look at our quantum results. Okay,
Oh, cool.
that's a little bit easier to interpret than the simulated results, unfortunately. But so what we're looking at here is go away. So what we're looking at here is I have to remind myself. So this was when we had the first polarization experiment, and this is when we were getting um, uh, right when we say we were blocking all the right-handed people. Okay, so what's happening here is that some of them got through in a perfect experiment like we just saw. We only saw one bin. That's because matplotlib went by default. If the bin is zero, it doesn't even plot it. And so we only saw one, but it was there. It was just zero size. So the 535 that we see here, this is quantum error. This is an error in the actual device itself. It shouldn't have been there. However, when we put that Hadamard gate in between, when we put that filter in between the left-handed and right-handed measurements, right, and we force them into the superposition of states, now all of a sudden we're seeing both state zero and state one. And this is not quantum error. I mean, sure, there are some errors in here as well, some false positives and false negatives, but largely we're seeing the effect of the superposition of that qubit before it's being measured. And that's why both states are restored. Let's see, what was this? This was the quantum coin toss. Okay, I mean, again, there's probably some uncertainty related to measurement, but this is also mostly statistical anyway. Lastly are the Bell states. So, of course, this is a misnomer. I only showed you one Bell state, although I have results for all four. This is the Bell state, the phi plus. So we should either be getting measurements. We did 8,192 measurements. On average, we should be getting half 0, 0 and half 1, 1. And so for the 0, 1 and the 1, 0 states, that's indicia that the Bell states were not properly prepared, or at some point before the measurement was made, those Bell states collapsed. No, I don't think I meant to do that, but yeah, there we go. So we're at 11 o'clock. Are there any questions?
So
So many.
I guess, given you're experimenting with it, it seems like there's a fair amount of quantum error still in doing the calculations. And I assume
Sure.
that's what the engineers are working on all the time, trying to minimize that.
Yes, absolutely. Yes, that is. Sorry about that. That is absolutely right. The biggest hurdle right now to quantum computing is twofold, really. It's the error rate, and it's also the number of physical qubits that we can put together. In order for quantum computing to really become, let's say, commercially viable, we estimate that we would need on the order of millions, 10 to the 6 qubits. And right now, the best that we're doing is 10 to the 4, really, and not even that reliably. So if you take a look at some of the results here, so uh, I didn't actually get to toggle the optimization levels, but when you do, you can see, for example, that you know the uh, the error rate. Let's take a look at Fez. This is the 156 qubits QPU. The error rate, I mean, we're talking about 95%. Like I would be satisfied if I got this in like my abstract algebra course, but 95% isn't really good when I don't know, it's obviously not the sort of reliability we expect from classical computers, but we're getting there. I don't do research in this field, and so my guess is the next is as good as the next person. But I would imagine within 5 years we'll see serious development in quantum computers. We're actually at the point now where they're giving away spare cycles for free, which I think is amazing. And if there's really one takeaway, I hope somebody thinks it's as cool, as interesting as I did, and just this is it's I wish that something like this were available for me 25 years ago. It probably would have changed the course of my career.
So if you go back to your map diagram you had up,
Sure. Which
the
let me
circle thing, yeah, wherever that
yeah,
was.
it's also one of my Zoom backgrounds.
So when you say that there's quantum error, is that because like we wanted it to go to the follow the red line down to the right, but instead of hitting right at the right, it hits somewhere slightly off? Is that kind of how I can imagine that?
Um
Because if that's spin and there's quantum error, then it must be an error in spin, right?
yeah, but it's quantum spin. So for example, quantum spin isn't actually spinning. We just That's just what we call it.
Yeah, the metaphor.
Yeah. So I wanted to put that out there first. Um, I think
Yeah, right.
the most common errors is not that we're not hitting where we want to hit on the block circle. Although there is experimental error there as well, right? Because a Hadamard gate, an exchange gate, a Z flip gate has to have a physical analog to be realized. So, the Hadamard gates that IBM is using, I believe they're using I believe that they're microwave impulses that are used to rotate or orient the spin of these physical qubits. I'm sure there's some experimental uncertainty there, but at the same time, I suspect they're also pretty good at doing that. Um, I think the experimental error that we see, or the problems that we see, are largely related to entangling larger and larger qubit states, trying to get, let's I'm showing very simple two qubit calculations, but here I can terrify you. I have some other notebooks that I didn't intend to present necessarily, but some of these actually, do I not have some? I thought I did. I have some. At least I've run some simulations. I wouldn't dare run them on a real QPU because I can't afford it. But I have some simulations of over 100 qubits, and so I can simulate that. That's fine. But how reliably I can create that state over and over again on a quantum computer, that's I think that's a whole different question. Also, I should mention too, when I'm doing shots, when I do those 8,192 shots, I'm asking the QPU to recreate that state over and over again, 8,192 times, and then make a measurement. And you can see that it only takes a couple of seconds or so to do that.
Hmm.
So the states don't have to live very long by our time scales, but that's still a pretty long time scale. To keep a coherent entangled state alive for, what could be tens or hundreds of milliseconds can be very difficult.
A question regarding your opinion on something.
Oh, I'm
Um,
the wrong person to ask for
uh,
that.
well, so I was thinking along the lines of quantum computing, um, at least right now, remains fairly limited in scope, I think. It's got applications in, like you were talking about, in areas like RSA encryption and I think some simulations with molecular docking and things like that. But do you see the scope expanding greatly? My understanding is they've talked about things like quantum machine learning and stuff, but there are serious hurdles there. Like you had mentioned, just because we have a state space that's exponentially bigger, we don't really get necessarily exponential speed up. We can't really measure 2 to the n amplitudes out of our result. And so for something like machine learning, I th right now I think we lose our theoretical speed up simply by encoding classical data into quantum states. Do you think we'll see the scope of quantum computing become more general, or do you think it's going to remain kind of niche in the problems that it solves?
Oh, my personal, well, I have to remind myself that I'm always surprised by the clever things people are
Mhm.
able to think of. And I mean, we could just point to, I think AI, generative AI, I think took everybody by surprise a few years ago. Um, I'm not sure. So I actually was intrigued by the ML AI applications of quantum computing too. Um, I'm not, it wasn't clear why quantum computing would be interested for people designing neural networks, although there is some discussion in the archives about that. I didn't dig deeply into that. It's actually the second bullet that hits a little bit closer to home for us, the cryptography and
Mm.
cybersecurity. Post-quantum encryption is something that we can do already. Like I said, that's actually part of TLS version 3. So you could start using quantum secure encryption, on your data today, right now, if you wanted to.
Mhm.
Um, the thing that I think is even more interesting, though, is the quantum key distribution. Quantum key distribution involves, well, you have to have it involves sending traffic along the internet using um, uh, well, quantum encryption, which these are quantum signals that can actually multiplex over classical fiber. And a few years ago, uh, Verizon, it was actually a few years ago, I think it meant 2021 or 2022, they actually set up a video stream using quantum key distribution, which is basically we're having quantum computers decrypt these keys on both sides of this connection, and set up basically 3 points where it was broadcasting video traffic or streaming video from DC to a couple different locations in Ashburn. And so I think this is actually really interesting for us because, well, for a variety of reasons, but yeah. So
That's
how
really,
quantum
yeah,
computing is going to be used in these other fields is anybody's guess. I mean, who
yeah.
knows? That's the grad students of today will figure these questions out tomorrow, perhaps.
Mhm.
Hopefully. So thank you so much, Glenn.
Mhm.
Thank you. This is a real honor. I was great opportunity to be able to share my hobby.
Yeah.
This was very cool.
So, hey, JP just ran into the room. So,
I just missed the whole thing.
Oh, like start over.
Yeah.
I know the script now.
stop the recording.